Ladies and gentlemen, please take your seats and silence your mobile devices. We will begin shortly.
It all begins from a single origin, a unique point in space and time. This is the spark of innovation, fueling your most amazing breakthroughs with the power of AI. It's a passion for discovery that unveiled the genesis of all that exists in the universe. Today, deep learning is helping farmers feed the world. And marine biologists save our most precious resources by analyzing in 1 month what used to take 10 years.
是谁发明了机械计算机？
Everyday devices translate even the most complex languages from voice into text and images into words.
Xavier is now present.
Helping the visually impaired recognize an old friend, or letting a blind woman read to her child for the first time. Autonomous vehicles give us the freedom to reimagine our city streets and deliver relief to those who need it most, even under the harshest conditions. We see robots teach themselves to perform simple tasks. We even watch as they tap into the power of deep learning to separate trash from treasure. And today, a 2,500-year-old game meets its match as a computer competes with one of the greatest human champions of all time, and wins. GPU deep learning is the breakthrough that sparked this AI revolution and fuels your most amazing discoveries yet to come.
Ladies and gentlemen, please welcome NVIDIA founder and CEO Jensen Huang.
Ohayo gozaimasu. Yokoso. Yokoso. Welcome to NVIDIA's GTC Japan. Our industry is going through some very exciting changes. GTC this year is a very exciting conference, and I'm so happy that all of you are here. We have much to share with you, so let's get started. I have been in the computer industry 35 years, and I've seen a lot of very exciting developments and a great deal of amazing changes. The changes in our industry transforms society. The importance of our work cannot be overstated. What causes the changes in every area of the computer industry is the computing platform and the computing architecture underneath. In early 90s, 1995, Microsoft, Intel created the PC, revolutionized the PC. Around that same time, Netscape and Yahoo brought the internet browser and search to the world. As a result, the PC internet generation was created. It put personal computers in the hands of 1 billion people during that time. Unbelievable revolution, unbelievable contributions to humanity. About 10 years later, the iPhone was created and introduced to us a computer that fits in our hands so that we can have access to mobile computing, to a computer all the time. Around almost the same time, Amazon AWS, the idea of putting a computer in the cloud so that all of our computing capabilities can be available wherever you are. A mobile computer, a supercomputer in the cloud. Introduced the world to the mobile cloud revolution. And as a result, almost 3 billion people now have access to computers. People who have no use for personal computers, people who don't understand how to use computers, can now also have the benefit of the computing technology we created. The mobile cloud revolution had enormous scale, introduced brand new companies, created a whole new wave of innovation, and there is no question it has transformed society and has made the society better. We are now at the beginning of a new era. For many of you, that's the reason why you came to GTC. You came to GTC so that you can learn, share your ideas, and understand what is happening in this new era, the new era of artificial intelligence. Artificial intelligence and IoT. In this new era, software will learn. software will write software. In this new era, machines will learn to reason. And there will be hundreds of billions of intelligent devices that are increasingly autonomous, that are connected to this incredible cloud computer, and all of it will be powered by artificial intelligence. So that computers will be seemingly intelligent and help us do things and solve problems that we frankly could not imagine just a decade ago. This revolution, the AI revolution, this era of computing, the AI computing era, has captured the imaginations of so many people, and it is in the process of going through almost every industry we know. This is the topic. This is the topic of this GTC. And GPU deep learning is what made it possible. How did it start and why did it start? How did it start and why did it start? Well, deep learning as an algorithm is incredibly powerful. It has the ability to learn to recognize patterns that are incredibly complex. For example, a human has eyes, eyebrow, eyelashes, ears, hair, mouth. However, so do monkeys and animals have eyes, eyelashes, hair, ears. So how do you recognize the difference between humans, monkeys, chimpanzees, and maybe even other animals? While us humans, we have the ability to recognize patterns with a tremendous amount of variables, with a tremendous amount of what we call dimensionality, a great deal of complexity. Humans have the ability to recognize complex patterns, to learn from the complex patterns ourselves. What are the most important features? Pattern recognition, feature extraction. Those are the two fundamental elements of intelligence. Pattern recognition, computer vision are based on those basic concepts. Well, for a very long time, computer vision experts have written very complicated algorithms to detect those important features, and from those features, understand what we see, pattern recognition. Well, deep learning has the ability to automatically learn what the important features are, hierarchy by hierarchy by hierarchy, edges to textures, to curves, to patterns, to objects, to eyes, head, body, human. Layer by layer by layer by layer, it can learn how to recognize very, very complicated things. Recognizing a human, recognizing the patterns of weather, recognizing almost anything in life. Pattern recognition is foundational to intelligence. Well, deep learning had this amazing ability to extract, to learn the patterns by itself. And it had one major handicap. And that handicap lasted for several decades. That handicap is it took too much computation to learn automatically from a large amount of data how to extract the important features. Well, in the early 2010, Swiss researchers in the Swiss AI lab and also in University of Toronto in Canada, researchers were simultaneously applying a new invention that they had discovered. And that new invention was a GPU, a general purpose GPU, based on a technology that NVIDIA invented called CUDA. They discovered that the GPU has the natural ability to process these neural networks in parallel. and provide 10, 20, 50, 100, 200 times speed up in learning from the data. And without the GPU, the training, the learning of this new neural net would have taken months and months. To develop software that takes several months is simply impractical. But their discovery of using a GPU made it fundamentally practical for the very first time. And then something happened that was very important. In 2012, a young researcher, Alex Kershevsky, working in Jeff Hinton's lab, wrote a very important paper and developed a very important network. And this network was called AlexNet. And AlexNet was trained on 2 NVIDIA GPUs, GTX 580. And it trained on 1 million patterns of images. And it learned from these 1 million images how to recognize objects. He submitted his network to a world competition. And the breakthrough was he won. With just several days of training, this network was able to beat the computer vision architecture and the computer vision algorithms developed by researchers over decades, refined over decades. AlexNet won the ImageNet competition. The results of that achievement caused AI researchers all over the world to pay attention to deep learning. Simultaneously, NVIDIA Research and Stanford recognized that in order to train important networks, and in order for us to really make a contribution to artificial intelligence, the networks we want to train have to be incredibly large. We want a big brain. Well, we developed the ability for multi-GPUs in a very large-scale computing system to train very, very large networks incredibly fast. That research was published also in 2012. Those 2 simultaneous contributions completely ignited GPU deep learning, and it triggered the beginning of what I believe will be the most important computer era of all, the AI computing era. Subsequently, researchers all over the world recognize now the importance of deep learning and how GPU deep learning could be very practical. Almost every university, almost every computer science department, almost every internet service provider, web service provider, recognized that they had an enormous amount of data that they could use to train very complicated networks. From Google to Facebook to Microsoft, one after another. And since then, almost every single internet service provider has adopted GPU deep learning for pattern recognition. The results are actually quite amazing. If you take a look at this chart, using hand-coded, hand-engineered, expert-coded computer vision algorithms, the results have now been completely eclipsed by automatically written software that wrote software to recognize patterns. And it has now achieved superhuman levels. A computer can now recognize images better than we can. A computer can now recognize images better than we can. Pattern recognition is also the foundation, of course, of speech understanding, speech recognition. Almost every speech recognition systems have now also adopted deep learning. And the results in the last several years have been incredible. Just recently, Microsoft speech researcher XD Huang and his team has achieved a result that is now 6.5%, 6.3% error rate. 6.6 error rate of speech recognition is quite a huge achievement, especially on this benchmark. And the reason for that is this. As you know, everybody talks a little bit differently. And also, speech that is spoken and speech that is read is very different. Because when I talk live, I make a lot of things like ums and ahs, a lot of false, unnecessary parts of the speech. Also, there are many letters in the English alphabet that's very difficult to discern. A, B, C, E, G, T, V, Z, all ends with E's, and they sound similar. And of course, background noise, quality of the microphones. There are so many things that make speech recognition very, very difficult, and there's a lot of noise in the background. And so as a result, humans have a very superior capability of detecting speech, but yet a computer has a very hard time until now. Until now. Well, in just a few years, in just literally 5-6 years, GPU deep learning has gone from a breakthrough in practical application to large-scale modeling capability to now achieving human levels of image and speech recognition. Image and speech recognition is the foundation, as we know, of learning, sight and sound. If we can see and we can hear, we can understand, we can learn. And if we can learn, it is the foundation of intelligence. And that is the reason why we believe the stage is set for the AI revolution. The stage is now set for the AI revolution. We have the computing model, GPU computing, and we have breakthroughs in the two fundamental pillars of intelligence. Well, why NVIDIA? Why us? What did it happen? Well, partly because NVIDIA is the world's largest parallel computing company. We have been working on parallel computing since the beginning of our company's existence. And the reason for that is that computer graphics, at its core, is the most parallel computing intensive problem. And so parallel computing has been at the essence of our company's soul since the beginning of our company. Several years ago, about 12 years ago, we invented GPU, invented GPU computing. We invented CUDA. That form of computing, we believed, could revolutionize many different areas of applications. We believed that there were many applications that were fundamentally parallel, and that our computing approach, if made general purpose, could make a huge contribution to the computer industry, and I think we were right. This endeavor that has now taken well over a decade, and for many in the audience, I see so many of our early adopters here in Japan. I thank you for all that you've done to make this new computing model a success. Well, what does NVIDIA focus on now? We focus on three fundamental things, and they're all powered by GPU computing. The first is high-performance computing, a field of computing where normal computers is not enough, where normal computers cannot address the problem. Scientific computing, of course, we just talked about deep learning. Computer graphics is certainly one of them. Second, visual computing. Visual computing. Computing the human perception of imagination. Computing imagination. How we imagine, what we imagine, computer graphics is a realization of that. Computing human imagination. And third, the work that we've done in the last 6-7 years, computing human perception. In a way, NVIDIA has become an artificial intelligence company, using computers to understand how the brain understands the world, and using computers to see the world. Using our computers to compute intelligence. We've become an AI computing company. Well, the pillars of our work, high-performance computing, visual computing, and AI, these three pillars of our work is going to come back over and over again during my talk. The thing that we're working on in focusing in this area is because we believe this is some of the most exciting areas in computing in the future. For the very first time, we are at the border of being able to realize what we've all known as science fiction until now. with visual computing, with high-performance computing and AI, we can bring to the world VR, AR, and the ability to interact with your computer as an intelligent agent. In the Iron Man movie, one of my favorite parts is whenever he's in the lab. And when he's in the lab, he's interacting with Jarvis. And Jarvis is his intelligent companion, fetching information for him, realizing the information in computer graphics, augmenting his view of his laboratory and computer graphics images. And of course, as this intelligent companion, he's collaborating with Tony Stark to create and invent something new. This image of the world, this possibility, I believe we are very close. And that is one of the reasons why it is so exciting right now to be in computing. Our company is a computing platform company. And you use the computing platform to make all of that amazing experience possible. It is you, the developers, the scientists, the researchers, the engineers, that take advantage of this GPU computing platform to realize these amazing experiences. GTC is our developers conference. GTC is the world's largest GPU computing developers conference. And it has grown tremendously in the last several years. You have realized the importance of this new computing model and the capabilities that it can provide. The growth is really quite extraordinary. We have decided, because of the incredible demand, to take GTC all over the world. And as a result, the expansion and the adoption, the attendees has grown so much in just a few years, 4 times. The number of developers that have downloaded our SDKs has grown incredibly, 3 times in just the last couple of years. But this is the amazing thing. GPU deep learning. The number of researchers of AI that has downloaded our software SDK and this platform so that you could do your work has grown 25 times. And I believe in just the 3 weeks that I have been on the road in GTC, this has probably doubled yet again. The number of GPU developers for AI is really quite staggering. And so the question is, maybe, why have AI developers all jumped onto GPUs? And I don't have a scientific reason necessarily for it. Why is AI and GPU perfect for each other? The computing model, of course, is very similar. But maybe there are some intuitive reasons why a processor that was designed for computer graphics is also the perfect and the ideal processor for artificial intelligence. And maybe the way to do this is, imagine if I ask you to think. Right now, if I ask you to think, and I ask you to think of a place where a good friend of mine is from, a place where a good friend of mine is from, I want you to think about Mount Fuji. I want you to think about Mount Fuji, please. When I ask you to think about Mount Fuji, I didn't tell you how to think about Mount Fuji, but I am pretty sure most of you saw an image of Mount Fuji in your mind. Your brain was a GPU. Your brain generated images called mental images. When I say think, you generated mental images. Thinking is generating mental images. Thinking is computer graphics. Maybe another reason is because our GPU is organized like a brain. Instead of one very powerful CPU, we have thousands, and in the case of supercomputers, millions of small processors that are working together to solve a problem. Maybe our processor is like a brain too. So a brain is like a GPU, and GPU is like a brain. Maybe that's the reason. But whatever the reason, this is a new computing model. And this new computing model is very different than the computing model of the past. In the past, software engineers wrote software and meticulously coded algorithms. Of course, we will continue to do that. However, the GPU deep learning computing model has different methodology, different tools, different flow, and different computing architecture. GPU deep learning is different almost in every way. And in order to take advantage of this new capability, software developers, including all of the ones at NVIDIA, in the last 5-6 years, we have retrained our software engineers and relearned how to develop new software for deep learning. It is a different methodology, it's a different process, uses different tools, and it runs on different computer architectures. It is a different computing platform. There are 4 basic steps, 4 basic stages of deep learning. The first, of course, is you need to have a deep learning architecture. And that deep learning architecture needs to be trained. Training the mind. It's a little bit like going to school. Training the brain. Training the brain requires an enormous amount of data, which requires an enormous amount of computation. Training the brain is the first step of GPU deep learning. Once you train the brain, you will have a deep neural network that is shown on top. That deep neural network can now run on computers of all kinds. That deep neural network initially will probably run in data centers. It would be a super brain that is running in your data center that can be served to many, many people. Maybe all of the people in your company, or maybe all of the people on the internet. So the GPU deep learning can now be in operation. The operation is called inferencing, to infer from the data what is happening, how to prediction, inferencing, to infer, not to deduct, but to infer, okay? That's called inferencing. And then the next part is maybe we would like to connect it to hundreds of billions of devices we call IoT. And each one of these devices will have a small brain inside, and they will operate and interact with the world. That learning will come back to the training again, to learn from the experience of all of your networks, to improve as you collect more data, as you have more experience. It will continue to learn. This cycle of learning is what's going to make artificial intelligence, quite frankly, grow faster than Moore's Law. Moore's Law has not stopped. I think we're going into an era where computing capability will go into hypergrowth because of this amazing learning loop that will happen from billions of devices learning from each other. This loop is fundamental to GPU deep learning, and this is something that is very essential to understand. Our conference and our company's responsibility, number one, is to create a complete platform that is end-to-end. Computers that is used for training, that is used for inferencing, and used for IoT. A software platform that is end-to-end. And to integrate with all of the tools in the world so that anyone who is doing deep learning can have immediate access to a very productive environment and have the ability to deploy your network into production. Our strategy number one is to develop deep learning end-to-end, end-to-end. Computing architecture, computing platforms, software, and integration with the entire world of deep learning ecosystems. So let me share a few examples with you. So the first part, of course, is training. Training is incredibly complicated, as we've mentioned. The networks are very, very large. Our brain has billions of neurons and tens of thousands of synapses connecting all the neurons. We have several hundred billion connections in our brain. And so ultimately, those networks are going to become that complicated. The deeper the network, the more dimensionality and the more complexity we can recognize. And so deep learning is going to require very large amounts of computation. However, training is billions of those operations multiplied by billions of iterations, because it takes billions of iterations to train the network. And so computation is incredibly high. But what's really amazing is this. Not only is the computation of deep learning high, it is also growing incredibly fast. In just a few years, from 2012 to 2015, Microsoft's network increased in complexity by 16 times. So the problem of deep learning is growing at a very high rate, much faster than Moore's law. So what started out having a very complicated problem initially is in fact growing at a very fast rate, at a hyper growth rate, because we would like to create very complicated and very large and sophisticated models. The amount of complexity is growing not just for the complexity of the network, but also the complexity of the data set, the amount of data necessary to train. And so deep learning, GPU deep learning, is really the ultimate computing challenge. And so the challenge then becomes, how do we as an industry keep up or even fuel this revolution? Well, we have to create computers that are increasing in performance at hyperlinear rates. We decided with Pascal several years ago that we would dedicate ourselves to drive the computing capabilities of our platform so that AI researchers all over the world can take this platform and advance AI as quickly as possible, because this is such a great potential for our society. And so we dedicated ourselves to creating the largest investment in the company's history, Pascal. Several thousand engineers worked on Pascal for 3 years. The total R&D budget was about $2 billion. It is the single largest computing endeavor in recent history. There are several major innovations of Pascal. The processor has been designed and architected for deep learning for the very first time. So even though GPUs was already good for deep learning, we applied everything we learned in the last 5 years to make our GPUs even more ideal for deep learning. We created a computer system from the ground up designed for deep learning. And as a result, the results are amazing. This is the GPU. Kepler is the GPU that Alex Kershevsky used for his breakthrough paper. Is right here. And this is Kepler, 65 times more powerful. And so a GPU is not just a GPU anymore. A GPU is a deep learning GPU. And then lastly, we dedicated a great amount of engineering to partner with all of the framework developers. These are tools for developing deep neural networks. We call them frameworks. Frameworks of all kinds, all completely optimized for NVIDIA's platform. So number one, the most important thing is training, step number one. However, step number two is, once you have a training network, a trained network, you now want to deploy this into production. Until now, most GPUs have been designed for training. Most GPU platforms have been designed for training. It is very, very powerful. It is very, very fast. However, in order to deploy the network into hyperscale data centers, we have to design specialized GPUs. These specialized GPUs have the ability to process the neural nets very quickly, of course, but also to be shared by many, many people. In the future, as these networks get deployed into data centers, hundreds of millions of people will access the internet, and every single query in the future will pass through an artificial intelligence network. A video query, a text query, an audio query, a live video share, everything we send into the internet will pass through an artificial intelligence network. We see a future where every single hyperscale cloud data center will have the ability to process all information through AI. And so we decided that we would create a brand new line of GPUs designed specifically for data center inferencing, and that's called the Tesla P4 and P40. It is 40 times the performance of the fastest CPUs, and is also 40 times the energy efficiency of the most energy efficient CPUs. And as a result, data centers can now support the queries, the artificial intelligence queries, the searches of text, the searches of images, the searches of audio, recognizing audio. And we can now inference for hundreds of millions of people in large-scale data centers very effectively. By adding just the Tesla P40, you can improve it almost immediately and so easily your throughput by 40 times. By adding a Tesla P4, you could improve your energy efficiency by 40 times. Okay? Very, very, very big deal. We just rolled this out, just announced this recently. We're sampling all over the world. On top of the Tesla P40 and P4 needs software. We have introduced a new piece of software, new software library called the TensorRT. It's a runtime accelerator that optimizes the neural network to be run on the processor. TensorRT is really fantastic. The networks are optimized, removing and optimizing mathematical operations, fusing operations in a horizontal way in one layer, or fusing across layers through different layers of the network. Okay? Auto-tuning. It has the ability to support different precisions from FP32 to FP16 to int8, and it supports all of the major image recognition networks, and we're going to continue to add more. And you can also customize your networks, and we can tune to that as well. TensorRT, it's available on our website. Please go and try to download that and enjoy that. Well, let's take a look at what we can do with all of this. We just talked about how we can use neural net to recognize patterns. We can recognize patterns. But we can also, as you know, humans can imagine. We can learn a style, and we can apply a style in our own artwork. One of the things we're going to show you is this is a network that was created by Artisto. And basically, this network does this. It learned from all kinds of famous art styles, maybe Picasso, and now it can recognize an image and apply that new art style. Recognize the image and apply the new art style. Okay? So we train the network not only to recognize an art style, but to apply the art style. And if you can do this incredibly fast, as I just mentioned earlier with our Tesla P40 and P4, if you can do this incredibly fast, you can even apply it to live video. And so what we're going to show you now, let's go ahead and run the demo, please. So first of all, we're just looking, this, I don't know how they do that. Japanese bakers have really fast hands. Okay, so these are some very beautiful images of Japan. These are just videos that are streaming into our computer. And so maybe what we could do now is apply a neural net to it. And so these neural networks were trained on art styles. Of course, not these video. It was trained on different styles of art. And then now we're showing it a new video, and we're asking this neural net, please draw this video based on that art style. Draw the video based on that art style. Isn't that incredible? Mount Fuji, so beautiful. Movies will never be the same. I could just imagine doing this for yourself. This is Picasso. This is how Picasso would have drawn and made a movie. Picasso style. And all of this is done in real time, and I want to show it to you. This is all done in real time. This is not pre-recorded. So let me show you. Hey guys, could we do live video? This is you guys. Oh, look at that. GTC drawn by Picasso. And wow, this is just beautiful. The audience of GTC are very beautiful. So, of course, if we could apply art to video, you could imagine all of the things that we could apply to video. We could teach our network to enhance the resolution. We could teach our network to remove noise. We could teach our network to eliminate blur. We could teach our network to insert, to add film grain. We could teach our network to do almost every form of video processing. So think about this for a second. For the image processing industry that has dedicated years and years and years of writing computer image algorithms, image processing algorithms, now we have a new tool. This new tool, we could train the network. Look at so many people. We could train the network. We could train the network to perform the necessary processing to enhance our videos, enhance our images. The potential is almost endless. Okay? Really, really exciting. All right, you guys. We better cut this. Thank you. Okay, so number one, training. Number two, inferencing. This is inferencing. The training of the network was done on high-performance Tesla-based, Pascal-based Tesla P100, and the inferencing is done on a Tesla P40. Okay, so training and inferencing. The ecosystem of the NVIDIA GPU computing platform, GPU deep learning platform, is really growing and growing very quickly. In fact, almost every web service provider and internet service provider and hyperscale provider has really adopted our GPUs for all of the work that they do. Almost every consumer applications in the future will be infused with artificial intelligence capability, because they service so many customers, hundreds of millions of customers. They have billions and billions of queries. The amount of data that's available to train their network is available. They just need to have a very fast, high-performance computing platform necessary to train their data. All of them have trained their data, their networks, with NVIDIA's technology, and now they're in the process of applying those networks into inferencing for large-scale deployment. You could also, if you were a startup and you don't want to have your own high-performance computer, our GPU platform, our GPU deep learning platform is now available on Alibaba's cloud, on Amazon's cloud. They just announced a very large deployment just a few days ago, IBM Cloud and Microsoft Azure. Microsoft Azure has said they have deployed so many GPUs that they believe they have the world's largest supercomputer now, based on NVIDIA GPUs. And so if you're a startup, or if you're a company that would like not to build your own high-performance computing data center, you can have all of these GPUs in the cloud. If you're an enterprise and you would like to do it on-premise, because your data is on-premise and you have too much data, maybe they're medical records data, maybe they're seismic data, Maybe they're data of your customers and they're available on premise, and you would like to have servers that were designed for deep learning. It's available from Cisco, from Dell, from Hewlett Packard, from IBM, from Lenovo. And if you were a startup, we're working with over 1,500 startups around the world. Over 1,500 startups around the world are using deep learning technology to create their AI startup. If you're a startup and you would like to have access to GPU platforms, the NVIDIA platform is available to you. So the GPU deep learning ecosystem is growing incredibly fast. This is the AI computing ecosystem, the NVIDIA AI computing ecosystem. And I'm really, really pleased with the way it's growing out. You basically can get access to NVIDIA's AI computing platform, irrespective of where you are, on any platform and in any way. You can buy it, you can rent it. Very, very accessible. Here in Japan, some really exciting work is being done. One of the most talented AI solutions teams, AI research teams in the world is actually based here in Japan, the Preferred Networks team. Really fantastic team. I think they're in the audience. I'm really proud of the work that they do. They've created a great platform and a great framework for developing neural nets called Chainer, and we're fully optimized for that. Rakuten does something that's really incredible. They have a flea market, and as you know, flea markets has tons of things, and there's no way to fully categorize them. By loading the images on top of their AI platform, they can automatically categorize all of the things that are inside a flea market, inside their digital flea market. And so if you're looking for small antique bottles, it shows up. If you're looking for plates, it shows up. If you're looking for toys, certain toys or dolls, it shows up. Okay? And so it has the ability to automatically categorize based on deep learning, based on artificial intelligence. Mizuho uses deep learning now to improve the accuracy of their financial prediction algorithms. And my understanding is that their improvement is actually quite significant. And in the world of finance, this is a very powerful capability, of course. Abijah is using deep learning to recognize patterns in retail. So customers that are going to the retail stores, they recognize where are they spending the time, which products do they prefer, and how can the retailer optimize the placement of their products and maybe even the architecture of their store to bring more delight to their customers so that their commerce can improve. A lot of really exciting things in deep learning. So far, I've talked about training and I've talked about inferencing. Now I want to talk about IoT. People have been talking about IoT for some time. One of the great things about IoT, of course, is the idea that we have smart devices that are all over the world with little tiny computers, and they could be integrated into our world in very nice ways, and they could be almost everywhere. However, the question is, how do you write the software for billions of devices? How do you write the software for billions of devices? Well, finally, we know the answer, and that answer is AI. AI is going to be the fuel. AI is going to be the energy of IoT. There are so many different IoT devices that are coming. For example, in the future, your home camera will not only record and you could see, but it can also recognize special things. So it will ignore most of the video until, of course, it recognizes things that are important to you. Maybe some special person is at the door, and the door opens by itself because it's your wife. Maybe it is watching to make sure that nobody comes into your backyard. However, if it's the wind blowing, or maybe it's the cat, or maybe it's the neighbor's dog, it doesn't matter. Okay? And so it has the ability to recognize what's important to you. If you combined a smart camera, an AI camera, with an AI microphone, you might have yourself a little cute family agent, intelligent agent. And this particular one is called Jibo, has the ability to talk to you, share, if you wanted to understand, know what the weather is, play some music, do a video conference call with your grandparents. It has the ability, you simply talk to it. Okay, so the number of ideas go on and on. This AI is going to power billions and billions of devices, and as a result, the IoT revolution is going to be fueled by that. We built a little tiny computer. Each one of these little tiny computers is essentially, thank you. We built a little tiny computer. It's called Jetson. Jetson, as you know, is the famous cartoon robot. This little tiny computer is called Jetson TX1. The entire architecture of Jetson is exactly the same as the architecture we have in the supercomputer. Exactly the same architecture shrunk into a little tiny computer. 10 watts. It's essentially a supercomputer in 10 watts and has special instructions and architecture for deep learning. What comes with Jetson TX1 is not just this module, but it's also all of the software that goes on top of it. So if you come to the NVIDIA website, the SDK is incredibly rich. Deep learning SDKs, computer vision SDKs, image recognition SDKs, and not to mention, the entire ecosystem of developers around the world are developing software on top of Jetson. So the software is going to be really, really rich. There are all kinds of applications of Jetson. There's some amazing ones here in Japan. As you know, Japan is the home of robots. This is the epicenter of robotic innovation. And I fully expect that here in Japan will be the major breakthrough of the future of where artificial intelligence and mechanical engineering, mechanical marvels come together to create future autonomous robots. Toyota has a robot that is used to help humans and help people around the house. There's all kinds of drones that are powered by AI, so it could look for things, it could avoid the environment, it could find its own way, and to hopefully deliver some goods or maybe deliver some medicine or find somebody who is lost. There's all kinds of robotic challenges here in Japan. Really fantastic. These little robots can see the environment. This is almost like a little tiny miniature self-driving car. Okay, so these little robots are going to be in incredible competitions. This particular robot is a soccer playing robot. And so if we can teach a robot how to play soccer, maybe someday the robot can also help us clean our house. Robot technology is not completely autonomous. Sometimes the robot technology can be integrated with humans so that it could assist us in carrying heavy things. Maybe it can assist us because we have lost our ability to walk. Maybe we're getting older. And so cybernetic innovations, where robotics and human capabilities come together. So this area of research is incredibly rich, and I'm super excited about it. The processor we've created for all of these applications, autonomous artificial intelligence applications, Jetson TX1, okay, for IoTs. Well, one of the most important applications of robotic technology is in one of the largest industries in the world. It's one of the most important industries in society. Without the ability of this capability, the Industrial Revolution would have never happened. As we know, the Industrial Revolution is about to go into a new era as well. One of the most important companies in the world of manufacturing is based here in Japan. FANUC is the world's leader in autonomous factories and robotics technology. Just an amazing, amazing company with a great history and, of course, enormous contributions to the world. One of the things that's so incredibly inspiring is the work that they're doing to revolutionize and to create the factory of the future. And the factory of the future will be powered by AI. In the future, robots are going to be able to work so much more closely with people. Robots will be able to articulate and have very fine motor skills. And these robots are going to be able to learn by itself. As we know, programming a robot for every single gesture, for every single movement, is incredibly difficult. Imagine writing a program for everything we do, for every physical action we take. That is essentially what a robot software programmer has to do. In the future, with the dream of FNUC, we can now have robots that will learn by itself, powered by AI. The AI robots themselves will be amazing, but they will be connected also into an AI factory. Their vision, FNUC's AI vision, is called FIELD. FNUC Intelligent Edge, Link, and Drive, FIELD. This platform is FNUC's AI computing platform. It connects factories, it connects all of the machines and the robots inside the factory into one artificial intelligent future factory. And the way that it works is very similar to the framework that I've already described to you before. First, it starts with training the FNUC brain. You have to train the FNUC brain, and that training is done on NVIDIA GPUs. Their researchers train the FNUC brain. That FNUC brain then can be applied into the edge, into the factory on the FIELD platform. And in the robots, they may have Jetson TX1s so that the robots themselves could also have AI computing capability. As a result of this platform and this approach to computing, they can now create the factory of the future. Let me show you a video of the work of FNUC. Isn't that amazing? I believe it's super ashi. Did I say that right? Okay. We are incredibly fortunate today to have Dr. Kiyonori Inaba to join us. I think, please. He is the head of the robotics division of FNUC.
Thank you very much.
The visionary behind the future factory, the artificial intelligence factory. First of all, Inaba-san, tell the audience, tell us, what inspired FIELD? What was the problem you were trying to solve? And what inspired the creation of this amazing platform for the future factory?
Future factory. So basically, in my understanding, the consumer on B2C, customers really tends to stick with their own preference, on taste. So in the point, we don't know what product for the future maybe, so we don't know what product will be manufactured next. So like customers might be able to place an order on their own design car.
Wow.
Then data will be transferred to the factory. Then manufacturing system try to including machine and sensor preference instruments, think how to manufacturing it by talking with each other. So that's the point. So that's the world. No programming exists anymore.
Can exist, yeah. And so this future factory, the robots in this future factory will have to be very flexible.
Yeah,
They have to learn from experience.
Yes.
Because you cannot program for every possible permutation.
That's right.
And these robots, maybe they have some basic skills, but when the requirement from the customer change, they can adapt to the requirement and still perform the skill.
Yeah, that's
Yeah.
right. So currently, robot moves. So try to move based on the fixed program. So if the order is changing, we need to create programming. So if there are several thousand of products we need to create, in that case, we create lots of cases. So it's really tough.
The utilization for the factory is very difficult.
Yes.
Yeah, so today the robots are trained for one task per robot.
Yes.
In the future, it would be great if the robots have many skills
Yeah,
and are very flexible.
that's right.
And then the utilization of the factory will be very high. Now, one of the things that you also told me about is this incredible ability for the robots now to learn skills by itself. And of course, there are many skills that are quite impossible to write a software program for. For example, a robot to come very gently to touch a very fragile product.
Oh, yes.
It is very difficult to write the program for that. And of course, they have robots, you have things, materials in the factory that have many different shapes, and some are very, very small. And so humans writing software for the robots is very difficult, but having robots learn by themselves is maybe a potential.
Yes. So as you say, programming writes programming. So right now, so in the point, in our feeling, we can automate 20%, 30% of all manufacturing process by utilizing this
Wow,
technology. Only. So our motivation is that, so how to increase this percentage? So I think there are three keywords. So first one is connectivity, and second one is almighty, so like multifunctions. Then last one is artificial intelligence. So IoT technology changed so tremendous. IoT changed our daily life and at the same time manufacturing way. So in that point, so regarding about connectivity, so talking about PC can connect to any devices, so such as printer, mouse, and etc. On the other hand, in manufacturing area still, so engineers and system integrators spend lots of time how to integrate various devices.
And so now with Fields, you can integrate and connect
Exactly.
everything inside a factory.
Yes.
Yeah.
So also about multifunction, so almighty as well. So like the PC can become any devices by downloading corresponding application. Like if you are going to download office-related application, they can be so become word processor and other devices as well. Then, so in smart factory, our goal is how to realize smart factory. In smart factory, probably, so by utilizing this technology platform, so we can so connect all the devices.
So that's
with a
amazing. So your
scale.
with Fields, a factory today is just a building with mechanical things inside.
Yeah.
But a factory with Fields in the future will almost be like a computer, and it will run software.
Yeah, exactly.
And so you will give this factory in the future more and more functionality, more and more skills.
Yes.
And the productivity of the factory and the value of the factory becomes higher and higher and higher.
So, but operator doesn't require so any special skills.
Right.
So it's really important point. But the point is that the number of connected devices increasing. So as the number of connected devices increasing, the amount of information to be processed is increasing. Edge computing is necessary for us.
And that's the reason why in your architecture of Fields, the computer is not just in the cloud. You need a supercomputer in the factory
Yes.
because you have so much data and you have so many new applications you would like to run in the factory.
Exactly. So in that point, our industry area is a little bit different from other area. So first one is responding speed. So machine and robots needs to talk with each other. But the talking speed, responding speed is really fast. 0.01 second, millisecond is necessary.
Basically, like you and I are talking.
Yeah,
So when I talk to the robot, you want the robot to respond right away.
yeah, right away.
Yeah.
Exactly. Supposing 4 robots are working together, so to pick up one work piece from the box, the most difficult issue is collision. So how to avoid collision? They need to know
Fast.
exactly.
They need to see each other, they need to sense each other,
Exactly.
and they need to perform, they need to react instantaneously.
Yes.
Yeah.
And then also, smart factory is composed of various devices. Of course, one of the devices robots, but the other probably machining machines, sensors, peripheral instruments.
Robot machines. Yeah.
Exactly.
Yeah, your platform called Robot Machines.
Yes, so many machines needs to talk with each other through sensing. So there are so many brains, as you say. So distribution. We need a technology distribution, real time, artificial intelligence.
Yeah.
So much computation. That's why.
And the software is impossible to write. It's too complicated.
Too complicated.
There's too much data. There are too many things happening. And so by using artificial intelligence and by putting your computing capability right in the factory, the robots and the machines can be very high performance so that they can respond instantaneously. And someday, they respond so fast that they can, in fact, work right next to a human.
Yes, that's another important thing. So still 20%, 30% of automation can be realized. But the rest of 70%, it's the manufacturing area where there are so many operators, human operators. So the point is that how robot can work next to human. So that's why we are working on collaborative robots.
That's really quite amazing.
Yeah.
Well, you know, not only is Fields and the work that your division is doing at FNAC, not only is it going to revolutionize the factories of the future, it's going to also expand the reach of your company into other industries. Because today, the manufacturing you do is very large industry, heavy industry. But there are many things that we want to manufacture that, that is not heavy industry, requires much more skills, much better motor skills, requires AI. Yeah.
Yes, right now our main market is automobile, 50%, but the other is general industry, 50%. But still, each segment is really small. So there are huge potential. So working, so by utilizing artificial intelligence.
Nothing is more satisfying than to do something that can revolutionize the industry and can be so good to society, but also a wonderful growth opportunity for your company at the same time, right? So Fields is just fantastic. It's a visionary platform. I'm so happy to partner with you. Thank you very much.
Thank you very much. I'm really excited to work with you to open the new door.
Thank you. Thank you, Inaba-san.
Thank you very
Ladies and gentlemen, Inaba-san. Thank you.
Thank you. Jason.
Incredible. I can't wait to see the future of robotics. And of course, AI Factory, you can imagine the number of industries globally that AI factories can impact. AI, as you can see, is already making a big difference, not just in consumer services, but in real industries, large industries, industries that moves the world. Speaking of industries that move the world, AI for transportation. Let me talk about autonomous vehicles. Robotics is central to, and the epicenter of robotics is here in Japan. The epicenter of the automotive industry is also here in Japan, where artificial intelligence, software that writes software, machines that learn, intersect with machines is incredibly exciting. And those two developments are happening right here in Japan. The transportation industry is $10 trillion large. It's automotives, it's trucks, as you know. It moves without trucks all over the world. It is very difficult for society to move and to society to exist. Trucks, shuttles, taxis, not to mention all of the supporting industries like the insurance. The automotive industry, the transportation industry, is one of the largest industries in the world, and it surely is one of the most important industries in the world. It provides us freedom. It moves the world. This industry has the opportunity to be completely revolutionized by AI. As you know, transportation or driving, the skill of driving is very complicated. There are a lot of very diverse amounts of information around the world. We are dealing with different circumstances all the time, and yet humans have a very natural way of driving. It is impossible to write software to drive. There are too many conditions. There are too many scenarios. There are too many things. And so the question that we have is, how can we apply artificial intelligence and GPU computing and GPU deep learning to revolutionize the automotive industry? I want to talk about using AI in three basic terms. One is perception. Perception is the first part of what we do. We sense what is happening around us. What is around us? Where are we? Perception. The second is reasoning. Reasoning. What am I seeing? What am I seeing? And what should I do about it? What am I seeing? What am I perceiving? And what should I do about it? Reasoning. In the case of a car, reasoning is, number one, where am I? What is around me? Where am I? Relative to all of the other things in my surroundings. And what should I do? Reasoning. Of course, one of the most important parts of reasoning in the case of self-driving cars is called localization. Where am I? And then third is taking action. Okay? Planning, driving, taking action. So these are the three phases of robotics. These are the three phases of artificial intelligence. These are the three steps, if you will, of self-driving cars. Perception, reasoning, action. Sensing, localization, driving. Okay? These three segments, I'm going to give you some examples in just a second. Now, as you can see, object recognition is not the same as autonomous driving. Object recognition is only just one small piece of the overall functionality necessary for AI driving. And so in order to do that, we have created an architecture for AI computing in the car. We call it Drive PX. It does sensing, it does localization, and it does driving. It does AI computing, and it does it all inside the car. We also created a scalable architecture. This scalable architecture was created because we realized that there are many different types of functionalities and different types of vehicles that requires autonomous capability. All the way from the basic auto cruise. Auto cruise is basically one little tiny computer based on Drive PX. It's in the car, and you can use it for autonomous highway driving. Auto chauffeur. Maybe in this particular case, we need enough computation capability and enough artificial intelligence software so that we can say, take me home, and the car will take me home. Auto chauffeur. And then, of course, full autonomy. This car will have no people inside, and so it can never make a mistake. And it needs to be able to handle almost every circumstance. And therefore, we need larger networks, more neural networks, and as a result, we need more computation. Full autonomy. We created one architecture that can span the entire range of the automotive autonomous vehicles that people want to create. We're working with 80 companies around the world now. Car companies, taxis as a service companies, shuttle companies, all kinds of companies. 80 different companies, startups, large companies, small companies. It's just the number of companies that are working on autonomous vehicles is really quite amazing. The computer is really quite small. This is Drive PX2. This is Drive PX2. This is the basic version. Little tiny computer has this called the CAN bus interface to the car, basically the bus of the car, connects to multiple sensors. And this is AI computing in the car. This is the computer. On top of it is a software we called DriveWorks. It is the operating system of autonomous driving. DriveWorks has several different parts, and it's basically a high-performance operating system for self-driving vehicles. It has several different parts, and I just want to show a few of them to you. The first part of DriveWorks is understanding what is around the environment. It is detection. It is using computer vision algorithms to recognize my surrounding and also localize your car based on the input of a HD map, localization. Localization, detection creates the environment around the car. We put that environment into what is called an occupancy grid, a data structure that is real-time updated with all of the surroundings of the car right now and the near future. Right now and the near future. The near future is computed using planning. We are estimating where all of the cars around us are, where all of the objects, and where will it be in the near future, including ourselves. Okay? So the occupancy grid contains the database of the surroundings of the car and the prediction of what it will be in the near future. The lower level is driving. This is called PilotNet. Detecting my environment, driving. Notice we now already have DriveNet, OpenRoadNet, and PilotNet. We have 3 different artificial intelligence networks, and there will be even more artificial intelligence networks in the future. And we'll keep adding it on top of this car, on top of this operating system, self-driving car operating system we call DriveWorks. But let me do this. Let me show you, number one, this first part. Okay, guys, let's show them DriveNet. Okay, so this is in California. This image, of course, it's the raw image of our cameras. So the quality of the image is what we give to the neural network, not for us to enjoy, but we're just showing you here. So that's why the image is the color is a little bit different. Notice we're detecting the cars in 3 dimensions. Okay, so 3D car detection. First of all, we detect the cars. Let's also detect the lane. Can we do that? So you can detect the lanes. Okay? But the important thing to realize is that when we're driving, we are not detecting a bunch of things only. We don't detect car, truck, tree, house, and try to avoid them. What we actually try to do is we drive to the safe places. Open road. Let's show them open road detection. So this is how we drive. When we're driving, we're looking for where can I drive to? And I can only drive to those places in addition to, but I'm going to avoid the cars. Okay? So driving is really about making sure that you have access to open roads. So this is called free space, and we're detecting all of this in real time on our Drive PX. Okay? And so let's go back. Thank you. Excuse me, let's put it all together. How's that? Okay, so we're detecting cars, lanes, and free space. And we simply taught the network to do that. We taught the network how to detect all of these things, and now the network is detecting it very naturally. In terms of computer vision speak, it's 3D detection and segmentation. All right, so detecting is the first part. Thank you very much, guys. Thank you. Thank you. So the first part is we detect and we localize, we figure out where we are based on, I didn't draw an arrow here, based on the input of an HD map in the cloud. The HD map is very, very important. So where are we relative to the map? What do we see around us? We update it into the occupancy grid, and then we visualize it. We visualize our occupancy grid. The reason why we visualize it is because I want to know what my car artificial intelligence see. I want to know what is in the brain, the memories of the artificial intelligence system. And so this allows me to visualize the occupancy grid. Guys, can we take a look at that? Okay, so this is visualization. As you guys know, we know quite a bit about computer graphics. This is also running on top of Drive PX. And so this is what's inside the occupancy grid. This is what's around the car. This is what's around the car, which means in the future, if this platform is very accurate, mirrors are not necessary anymore. I can see everything around this car. I can see the car, I could see the traffic, I could see everything around the car, and I could see it from multiple viewpoints. Okay? We're tracking the car, we detect the car, and we track it all the way around our environment on this occupancy grid. Can you guys see that? So we detect surround detection and update the occupancy grid, visualize the occupancy grid, and so this is what the car sees. Pretty amazing. In the future, no mirrors will be necessary. Okay? Thank you. Now, of course, this is the first part. This is the first part. But remember, how do we drive? Steering. Steering is, as you know, for all of us, there's no equation for steering. We have no equation for steering. There's no F equals ma for steering. There's no V equals IR for steering. Steering is a behavior. We just steer. And so, what if we taught a network how to steer? Without any information, we simply taught our network how to steer. What I'm going to show you is this. This is a car. It's called BB-8. This is NVIDIA's car, our little robot car. It's an AI car. And this car only has camera input and it's steer. Watch us steer. Using imitation learning, it is learning from us. We drive and the network learns. And we keep driving and the network keeps learning. And we keep driving and the network keeps learning. And we have no idea what we're teaching the network. The network is simply learning from us. Okay? Now, before I show you the video, I just want you to know there's no detection happening. It's simply camera in, driving. Camera in, driving. No software was written. This car learned how to drive completely by itself. Okay? This is an AI car. Could you please roll it?
Oh yeah, good. The universal sign for auto.
Notice there are no lanes. No signs. BB-8 is learning. Oops. No cone detectors. No lane detectors, no car detectors. Just drive. Look at his hands. Wow. No software.
So cool.
How do you write a software for this? No mistakes. Merge onto traffic by itself. No lane detectors. You can see the rain. It's raining at night.
Got it.
Incredible. This is the power of AI. And I think the Japanese word for it, this is definitely subarashi. There's no question. This is AI. So the question is, the question is of course, what did BB-8 see? Would you like to see what BB-8 see? It saw something. It saw something. We taught it to learn, and then now we're going to visualize its brain. We're going to take the brain and we're going to draw it for you. Okay? So this is, let's take the video. This is the visualization of BB-8, what BB-8 saw. It learned how to see that by itself. Simply because by driving, it found, it detected, it extracted the essential features for steering. The feature detector of an artificial intelligence network of deep learning can now detect, based on what we decide to do, but what we did, what the important features are that led to our actions. And notice, these are the things that it saw. It saw some lanes and it saw some edges of cars. Hey, let's go to the country road, please. This is country road, okay? Can you guys see this? It's detecting, oh, it saw the bushes and that's why it steered away from it. It saw the bushes, steered away from it. It's looking for the lane, it saw the lane. So when it made that decision, these are the important features that it detected. When it turned, those were the important features that it detected. And you could see it saw the pipes. And it realized you got to drive away from that. All by itself, based on artificial intelligence. Okay, guys, thank you very much. Good job. And so how do we connect all of this into DriveWorks? We start by letting the car drive. We start by letting the car drive. And by detecting the surroundings. Is it safe to drive? Is the lane safe to drive? Do we detect cars and other things around it? Based on that, we can apply brakes. Okay? And so continue to drive unless you detect it is not safe, unless you detect there are other objects in front of you. And then that's when you apply brakes. And so as you can see, we have multiple networks that are happening, that are running at the same time. And over time, I think we'll have more and more networks. One of the most important things that was fed into BB-8, what's fed into the DriveWorks operating system, which we are now releasing, called Alpha 1. This release of software for all of our DrivePX partners will get the Alpha 1 release in a very near future, in a couple of weeks, and then we will update it every 2 months. These artificial intelligence network will continue to be updated over time. One of the most important parts of this is the HD map, and we're working with mapping companies all over the world. You use our computers, use DrivePX in the car, you use the Tesla GPU systems in the cloud. The GPU system in the cloud is for map processing. The DrivePX2 in the car could be used for in-car mapping, continuously mapping and updating the map. Okay? And this entire platform is open. So that once we connect it to HD map companies all over the world, we're partnered with Baidu in China, we're partnered with TomTom in Europe, and we're going to partner with mapping companies all over the world, so that every single car in the world will have access to HD maps. We're partnering with them to create an end-to-end system from cloud to car for the very first time. An autonomous computing platform from cloud to car. HD map, the autonomous operating system, the AI networks, and the AI supercomputer in the car. The entire platform is now integrated. Okay? So, DriveWorks. We're focused, as I mentioned earlier, at the intersection between computer vision, visual processing, HPC, high-performance computing, and AI. This intersection, I believe, will be the intersection of some amazing progress and amazing developments in the future. Robotics, of course, is one of them. Autonomous vehicles is another. There will be many other applications that are residing in this intersection. In the last several years, because we realized how important this area is going to be, we decided to dedicate ourselves to building a processor designed specifically for this intersection. This processor we're introducing today is called Xavier. Xavier is the most ambitious single chip computer that we have ever done. This is the largest single chip computer I believe the world has ever done. Xavier is 7 billion transistors. It is larger than the largest server class Xeon processor. Thousands of engineers are working on Xavier right now, and it has several characteristics that are just really important. It's 7 billion transistors made of 16 nanometer 3D FinFET. It has 8 very high performance CPU cores. And the reason for that is because AI computing is not just about the neural network. AI computing requires high performance computing throughout. Still a lot of code to do. And so 8 core custom ARM64 CPU. 512 next generation GPU cores. And it has a new computer vision accelerator for computer vision processing like SLAM and stereo processing. And it has a really high performance video processor. And the reason for that is because every single car in the future needs to have a very high quality black box. It needs to record every single camera and for just in case. And it's designed for ASIL C functional safety. Okay? So this is the largest endeavor in our company's history and the most complex single chip computer that the world's really ever done. Now what's really amazing is this. It's going to replace the highest configuration, highest performance Xavier with 4 processors. 2 Pascal GPUs and 2 Parker SoCs will be replaced by just 1 Xavier. So 2 Parkers and 2 Pascal GPUs, 20 tera operations of deep learning, 120 spec-int. This is about the performance of about 100 MacBook Pros. Okay? So this little supercomputer will be replaced by literally 1 single processor called Xavier, and it will just be 20 watts. Ladies and gentlemen, Xavier. So this is it. This is what we talked about today. Our company is dedicated to this new form of computing called AI computing. And we want to make sure that this computing approach is available to every single industry. And it starts out, number 1, by creating an end-to-end computing platform that includes training, inferencing, and IoT, and all of the software that sits on top of it, and the integration into the world's deep learning frameworks. Number 2, I announced the release of the upcoming DriveWorks Alpha 1. It is based on our DriveWorks operating system for autonomous vehicles. I demonstrated several of the artificial intelligence networks and the computing platform that it runs on top of. DriveWorks Alpha 1 will be available in late October, and we will update it every couple of months. We announced our partnership with Fanuc, the world leader in robotics and factory automation, as we build the future factory. And then lastly, we introduced the future of AI, the future of autonomous machines, Xavier, the largest endeavor SoC, the largest endeavor single chip computer we have ever undertaken. I think it's very clear that AI is going to play a very large role in society. This is a brand new computing model. This brand new computing model requires us to relearn computer software from beginning to end. However, the implications of this new computing approach allows us to solve problems that you can see that simply wasn't possible by us writing software with our hands. Now software will write software and machines will learn. The implications of that is really extraordinary. Here in Japan, the automotive industry, the healthcare industry, as well as the robotics industry, I think can be completely revolutionized as a result of AI. I'm so happy to see all of you at GTC. I think this is going to surely be the landmark GTC, and it's going to be the first GTC that is going to attract so many new AI researchers here in Japan. I look forward to working with all of you to create this future. Thank you very much. Arigato.